Welcome to this explainer. You know, we interact with computers constantly, literally all day, every day. But how often do we actually stop to think about the physical reality of what's happening inside the box? Today, we're going to change that and demystify the abstract, microscopic magic happening right under your fingertips. So, what actually happens in the exact millisecond after you click your mouse? Let's dive right into this by tracing a highly relatable action, just clicking an icon to open a web browser, all the way down into the processor. Because in that tiny fraction of a second, an unbelievable sequence of electrical and logical events takes place. Section 1. The anatomy of computing. First things first, we need to establish a quick map of the physical territory inside your machine. Think about it like this. Every single action flows from an input device, travels through an interconnection network, and hits the processor and memory. Whether we're talking about a massive supercomputer or just the smartphone sitting in your pocket, digital systems are built on these distinct functional units. Your mouse sends an electrical signal, sure, but before the processor, the real brain of the computer, can do anything with it, it has to be translated. Which brings us to Section 2, speaking the machine's language. Before the processor can act, your intent needs to be translated into hardware terms. Now, it's absolutely fascinating to see how software gets compiled down to binary machine code, which the CPU essentially reads as physical high and low electrical voltages. We start way up at the top with high-level languages, the human-readable code that programmers write, like an if statement. That gets translated into assembly language, and then an assembler converts that into raw binary machine code. At the deepest physical level, those ones and zeros aren't even numbers. They're literally just instructions telling microscopic transistors to turn an electrical current on or off. Section 3, the fetch, decode, execute cycle. Once that code actually hits the memory, the processor kicks off an endless, rapid-fire loop to carry it out. This whole concept perfectly illustrates the von Neumann architecture. Since the dawn of modern computing, machines have relied on this stored program idea, operating in a continuous loop between the control unit, the arithmetic logic unit, and RAM, where both instructions and data share the same physical memory space. So, the absolutely crucial takeaway here is that every single instruction strictly follows four hardware phases: fetch, decode, execute, and write back. That is exactly how code turns into action. Section 4, inside the CPU kitchen. Now, to make these abstract concepts crystal clear, let's just imagine your CPU as a highly organized restaurant kitchen. By mapping these technical terms, we can see the RAM is basically a giant recipe book. And the CPU? Well, that's our chef. Fetching is the chef walking over to read the next line of the recipe. Decoding is figuring out exactly what bowls and ingredients are needed. Executing is the actual mixing of those ingredients. And finally, the write-back phase is plating that finished dish for the customer. Now, just like a deli worker pulling the next numbered ticket from a queue, the program counter ensures the CPU never loses its place. A lot of people get this mixed up, so remember, the program counter doesn't hold the actual instruction itself. It only holds the exact memory address of the very next instruction to be fetched. It's constantly looking to the future. So, the program counter hands that address over to the memory address register, or MAR. And the requested recipe line gets delivered straight to the memory data register, the MDR, which basically acts like a physical loading dock for incoming data. Next up is the decode phase. Here, the control unit steps up, acting as the head chef. It analyzes the instruction's opcode, which is the action to take, like add or move, and the operands, which are the ingredients. It then sends out precise electrical signals to configure the rest of the CPU. Then, we hit the execute phase. This is the actual cooking. The arithmetic logic unit, or ALU, processes the mathematical computations and logical decisions. It performs the math or evaluates logical conditions, fundamentally changing the flow of execution based on what it finds. Finally, we have the write-back phase. This is all about consolidating those calculated results safely back into internal CPU registers or external RAM. If we skipped this step, everything the processor just worked so hard to calculate would instantly be lost the second the chef turns to the very next ticket. So tying it all back together, when you clicked that browser icon, your operating system moved the binary code to RAM. The PC queued the start address, and the CPU furiously looped this exact cycle to literally draw the browser window on your screen. Section 5, the power of pipelining. Let's see how this builds into an incredible technique modern processors use to absolutely maximize their speed. Because doing things one step at a time is simply way too slow for today's computing, modern CPUs actually overlap the phases in a continuous flow. Instead of waiting for one instruction to finish all four steps, while one instruction is being written back, the next is executing, another is decoding, and a fourth is already being fetched. Basically, pipelining transforms our solitary kitchen chef into a massive, high-speed industrial assembly line. It executes multiple instructions concurrently, making sure that no part of the hardware is ever just sitting idle during a clock cycle. But of course, this concurrency introduces complex risks called pipeline hazards. These are control or data conflicts that happen when overlapping instructions depend on previous unfinished results. When that happens, the processor might literally have to guess the future using branch prediction, or just stall the entire pipeline completely. To keep this gigahertz speed assembly line fed without stalling, processors rely heavily on built-in cache memory. Ultrafast L1, L2, and L3 caches are built directly onto the silicon to completely bypass the agonizingly slow trips out to the external main RAM. And what about multitasking? Well, to jump from your browser over to an email app, the CPU performs what's called a context switch. It packs up its current state, saves it safely to RAM, and instantly loads up the exact state of a totally different program. It happens so fast, it creates the illusion of doing a dozen things at exactly the same time. It is absolutely staggering to realize that the machine repeats these exact steps forever, billions of times per second. Every single pixel, every sound, every click relies on this relentless microscopic rhythm. But, if we're already doing this billions of times a second on a microscopic scale today, what exactly happens when we hit the absolute physical limits of silicon tomorrow? Thanks for joining me on this explainer. Keep wondering and keep exploring.